Chapter 4.1 consists of 5 parts, and in this video I will only focus in the first 3, which are concepts of limit, continuous functions, and the limits of continuous functions. Let's look at the concept of limits first. Consider fx equals to x squared minus 9 over x minus 3. The first question is, what's the value of f3? To find f3, you put x equal to 3 into the function, and then you will find the denominator becomes 0. So the value is undefined. How about if we are not going to find f3, but the value of fx when x approaches 3? Is there any difference? Let's use the table below to find it. If we consider x is 2.99, then you will find fx is 5.99. How about if x is more closer to 3, which is 2.999? Then you will find this is 5.999. Then this is x is 3. Then already know that it is undefined. How about if it is bigger than 3 a little bit, which is 3.001? Then you still can find the value. Similarly, you get this. As you see that from the table, when x is approach 3, fx is actually opposing a number. Which is 6. So we can find, actually we observe that when x approaches 3, fx approaches 6. Bear in mind, we just say approaches, but not equal to 6. So in this case, we write when x approaches 3, and it says the limit of this function is equal to 6. Here are some remarks. Remarks 1. H approach 3 actually means x approach 3 from the left and also from the right. Remark 2. You have limit x equals approach 3 of fx equal to 6, but fx is undefined in this case. So in general, a function fx approaches a number L. When x approaches a, then we write in this way: limit when x approach a, fx equal to the value L. It is very important, so I remind you once again, fa not necessarily equal to 0. Just in the case we discussed before, f3 is undefined but not equal to L, but not equal to 6 in that case. Let's look at some questions. In each of the following, determine whether the given limit exists. If the limit exists, write down the limit. For question 1, when x approach 3, you will see from the left hand side, fx is approaching 4, and from the right hand side, fx is also approaching 4. And also in this case, f4 is also exists, f3 is also exists, which is equals to 4. So limit of the fx exists as equals to 4. For question 2, you see, when x approach 2 from the left hand side, it's go to 3. It's approaching 3. But from the right hand side, it's approaching 7. Because these two are not matching, so the limit does not exist. For question 3, you see from the left hand side, when x approaches 0, it goes to negative infinity, means a very, very small number. And from the right hand side, it goes to positive infinity. It means a very, very big number. So the limit does not exist. For question 4, in this case, we find f5 not exist. And you see here, there's a hole there. It means it is not exist there. So f5 does not exist. Okay, but if we see when x approach 5 from the left hand side, it's approaching 2, and from the right hand side, it's also approaching 2. So in this case, we also say that the limit exists and equals to 2. Let's go to part B. Part B, we are talking about continuous function. Continuous means it is not broken. So consider any functions, we can draw it, okay, without broken, and it is a continuous function. Let's consider this is A. We make it shorter, okay, so you can redraw it again. You can. It's a continuous function. This is A, and this is B. Let's make a point C here. Because this function is continuous, so okay, it actually continues at any point. So we can say y equals to fx is continuous at x equals to c, because it is at c it is continuous. And we also can say that actually this is continuous at any point. So we write the interval from A to B. Okay, we use a round bracket, okay, to a small bracket to represent. There are many continuous functions. Here are some common types. Polynomials, a radical, like a third form. An exponential, it means the x is in the power. Logarithmic functions, and also trigonometric function. There's only sine and cosine. Okay, later we will talk about tangent. Okay, on the other hand, if a function is broken or has a hole at x equal to a, then the function is said to be discontinuous at x equal to a. Just like the first example we discussed, it is discontinuous at x equal to 3. And if it is discontinuous at any point, then the function is called a discontinuous function. Here are two examples. Example 1 is what we discussed before. It is a continuous function, which is discontinuous at x equal to 3. And I also give you the second example, tangent x. As you know, tangent power over 2 is undefined. So actually the graph of the tangent is like this. This is power over 2. So you see, this is discontinuous at power 2. And finally, we go to the limits of continuous functions. If a function is continuous, then from the left-hand side to the right-hand side, and its value at a is also exists. It is quite obvious that the limit x tends to a, fx is exists, and also it will be equal to fa if fx is a continuous function. Remember, this is very important. Only continuous function has this like feature, and this is actually theorem 4.1 in your textbook. So here are all the explanations of section A to C. And now please try to do the quick practice 4.1 on page 4.7. I will show you the answer in another video.